Welcome back. In this second part of our demo video series, we'll discuss how to build our model's features, X Vars, and the target variable Y var. The target variable in the model is the residual returns over the n-day horizon. It is given by the following equation. Let be our target variable on day. This is defined as the sum of daily returns from day to day. For example, on January 2nd, the 5-day future returns are computed as the sum of daily returns from January 5th to January 9th. To account for lag in the available data on January 2nd, as well as the time to model and enter the position, the return for January 5th is skipped. Thus, we only sum the returns from January 6th to January 9th. The following days are computed similarly using a rolling sum. We train on horizons longer than 1 day, even though the signals will be evaluated against 1-day future returns. This approach smooths the target variable or Y var and reduces its volatility. X vars are the features used as inputs to the model. The goal is to transform raw datasets into useful features, creating 2 datasets. These are XY train, used to train the model, and X predict, used to generate predictions from the trained model. Several constraints guide the predictions and features. These are causality. Predictions on day must depend only on data available on or before day. Look-ahead bias must be avoided. Then, primary keys. The combination of date and CWIQ code must be unique. No duplicate date and CWIQ code pairs are allowed, and no nans should appear in these columns. Finally, no missing dates. Predictions must exist for all dates within the dataset. And prediction volume. At least 1,000 predictions are required per date. Here are some useful guidelines for creating effective features. Again, causality. Ensure no look-ahead bias. Avoid shifting features backward in time. A simple check is whether your model can still create predictions on the last available date without reading future data. The provided scripts handle date calculations to prevent this issue by default. Then, stationarity. Ensure feature distributions remain consistent over time. Normalize features to keep the model's training distribution stable. Additionally, diversity. Aim for numerous uncorrelated features. Use cross-sectional and rolling transforms to create varied feature sets. Models like LightGBM handle collinear features well, but diversity helps. And density. Minimize missing values, nans, zeros, or sparsity in features. And finally, meaningfulness. Use domain expertise or common sense to design interpretable and contextually relevant features. Step 0 is to derive, train, and predict date ranges. This is labeled as Step 0 as this will be done automatically by the MyAlphaPipeline class, but it needs several arguments. It needs the following arguments. Start_predict. This is the start date when you want your predictions to begin. End_predict. This is the end date of your predictions. Train_look_back_years. This is the number of years of data used to train the model. X_days_look_back. This determines how much additional data needs to be read. To understand X_days_look_back, we need to understand how alphapipeline.py knows how much data to read. When you pass start_predict and end_predict to alphapipeline.py, it automatically determines how much data it needs to read using train_look_back_years. For example, if you want to produce predictions for the month of January 2016 with a model that uses 1 year of data and has a holding period of 5 days, the model needs 1 year's worth of data shifted 5 days back. Recall that we need to skip the last 5 days to avoid look-ahead bias. In this case, given a start_predict date of January 1st, 2016, and an end_predict date of January 31st, 2016, with a 5-day holding period, train start date is December 23rd, 2014. Train end date is December 23rd, 2015. Inside my alpha pipeline, the identify_adjusted_train_dates function is used to do this computation. However, if there are transforms that use a window, e.g. mean over the past 60 days, on top of the 1 year worth of data, it needs an additional 60 days of data. This ensures that on the first 60 days of training, the 60-day mean values won't be nan. For example, if we only read sample data starting from the train start date and compute a 60-day rolling mean for feet_02_sub_01, the first 60 days of the transformed feature in the training period will be nan. If we read sample data starting from the train start date plus 60 additional days and compute the 60-day rolling mean for feet_02_sub_01, the first 60 days of the transformed feature in the training period will not be nan. To instruct alpha_pipeline.py to read an additional 60 days of data, x_days_look_back must be passed and set to 60. Step 1 is to read the datasets. Several datasets are made available to participants. Participants are allowed to choose all or a subset of these datasets to build their model. To read a dataset, participants will use the readData function inside utils.py. This function takes in the complete path of the data to be read. Date columns. Minor date. Participants should note that each dataset may have different unique keys, so they may not necessarily have unique date and quick code out of the box. Also, not all datasets become available on the first day of in-sample training. In this case, minor date should be defined and set as the first date the data is available. This prompts the function to ignore errors when it encounters missing dates before minor date. You may refer to the datathon mechanics for more information on the datasets. Step 2 is to merge all datasets into a single data frame. We will call this dataset XOR_DF. Here, you should ensure that none of the constraints mentioned previously are violated. For example, you may want to check for duplicate keys in XOR_DF. Step 3 is the most important part. Participants will likely spend the majority of their time iterating over this step. This step is where transforms are applied to features in XOR_DF to get useful features. Predefined transforms are available to participants, which can be found in the transforms.py file. We'll go through them in more detail in the following slides. Again, you should also ensure that none of the constraints are violated. Take care not to read future data or introduce duplicate keys in your transforms. The final set of features, called x__, should all be numeric values. The next step is to create the construct_features function, which will later be transferred to alphapipeline.py. As mentioned earlier, the major task for this datathon is feature engineering. Pre-built functions are provided under the transforms.py script. All the transforms included in the transforms.py module have the following general structure. Input data frame. This data frame should already satisfy the constraints we mentioned before, e.g., no duplicate keys, no look-ahead bias. List of columns. A list of columns of the data frame on which the transformations are applied. Transform-specific arguments. These are additional arguments specific to the transformation. Optional suffix. A string that gets appended to the transformed columns. The default value of this suffix depends on the transform. When a transform function is used, the expected output is the same as the input data frame but with the new transformed columns. The functions in transforms.py can be divided into two types. Cross-sectional transforms. These transform the values of a stocks feature by taking into account the values of other stocks on the same day. All the transforms under this category group the rows by date and then apply the transformation on all the stocks available for each date. This prevents values from other, potentially future, dates from affecting the values of the current date. You may also do further grouping on some categorical column, e.g. sector, by changing the group_by argument. This groups the data frame by both date and sector, then applies the transform on each resulting group. You do not need to specify the date column in the group_by argument, as this is already implied. Examples include demean_by_date, subtracts the group mean from the feature. Median underscore by underscore date. Score underscore by underscore date. Rank underscore by underscore date. The other type is time series or rolling transforms. These transform the value of a stock's feature by taking into account its past values over some fixed window. Internally, this first sorts the data frame by date to prevent look-ahead bias, groups it by CWIQ underscore code, and then applies the transform on a rolling basis on each of the groups. All rolling transforms require an integer argument window, the number of past days considered, and an optional integer argument min underscore periods, the minimum number of observations required for a valid value. For example, if the window length is 21 and there are only 15 valid values in the window, due to nans or proximity to the start of the series, having min underscore periods greater than 15 will result in nan for the corresponding row. Min underscore periods defaults to none, which is the same as setting it equal to the window length. Participants may want to set it to a value less than the window length to prevent too many nans. Examples include rolling underscore to mean, rolling underscore median, rolling underscore score. Participants can build their own transforms by building on top of these existing ones or constructing custom transforms tailored to specific datasets. The transforms we have assume that inputs are already unique in date and CWIQ underscore code, but there may be useful transforms on raw, unduplicated data that yield better signals. This concludes the section on building model features and the target variable. Now that we have our model inputs, we can proceed with training the model, which will be discussed